That's fine, thank you. All right, so yes, as I was saying, most of you will be aware we're trying to unify the benefits of System 1, System 2 style thinking. And in this talk, and indeed many other sort of approaches, we're making the assumption that we can implement System 1 with a neural network and System 2 with logic. And what we're doing is trying to use the neural network to perform perception from unstructured data and then use a logic-based system to map these perceptions into sort of higher level, higher order decisions. So a lot of the work in Neural-Symbolic AI is based around something called Neural-Symbolic reasoning, which is all about using the logic to try and help train the neural network in a better way. So that might be constraining it with respect to some background knowledge, or it might be using weaker supervision to actually reduce the amount of labeled data that you need in training. But the key question is, where does this knowledge actually come from, as currently it is manually engineered by humans? So in my line of work, I'm aiming to go in the opposite direction to neurosymbolic reasoning and move towards neurosymbolic learning, where we're learning this knowledge instead of requiring it to be manually engineered. And what we can do is then learn sort of interpretable logic programs as a set of rules, which I'm calling a hypothesis, from unstructured data, such as images. So along similar lines to what Richard was talking about this morning. Now, the challenge, if you do this integration, which at the moment we're using pre-trained neural networks, which is, again, maybe a little bit naughty if you were listening to Richard's talk. But actually, this is not necessarily trivial in terms of rule learning, because the images at the far end would be vulnerable to distributional shift, which that means when you move downstream to the symbolic level, you're potentially dealing with incorrect predictions made with high confidence. So in our architecture, what we're doing is we're starting with a set of images, a collection of images as input on the left-hand side, as well as a downstream label for the final task, some background knowledge if you have any, and a search space for the potential hypotheses that you might want to learn. And we feed these images into a pre-trained neural network that returns a probability distribution over the classification for potential concepts that are in the image. And then we implement the interface between the neural and the symbolic component using a data to knowledge generator called D2K for short. This really transforms the neural network output into a symbolic representation with sort of two key pieces of information. So firstly, we map the predictions of the neural network into a symbolic form, and that can also be associated with some metadata that you might have in symbolic form about the images that you have. And then also, secondly, we transform the neural network confidence output into a weight penalty for the symbolic learning system. So you can think of this weight penalty as indicating a level of noise on the neural network predictions. So the next step is sort of quite straightforward. Once we have this information, we can then create training examples for the symbolic learning system and then learn the hypothesis at the end. So as an example, consider this Sudoku grid validity task where we have as input MNIST images arranged into the grid and a label indicating whether the grid is valid or not. So the first piece of information, symbolic information that the D2K is generating is our neural network predictions and associated metadata. So we have the predictions here in symbolic form in F. These are the values that have come out associated with each image in the grid. And our metadata is giving us row and column coordinates so that we can identify the location of images in the grid. And the second part with the confidence, then, so let's assume the neural network here outputs these probability distribution or confidence vectors at the top here, one for each image. We then take the best prediction for each image and use t-norm confidence aggregation to create a single unified weight penalty that represents this example. In this case, we're using the Gödel t-norm. And if you have these confidence scores here for each image, you get a weight penalty of 0.77. So at this point, we have our predictions and metadata in symbolic form. We have our weight penalty. We need to create a training example. Now, the method that we're proposing is general enough to support any ILP logic system capable of learning from weighted examples. But in this work, we're using the ILASP and FastLAS systems that are based on the learning of answer sets framework. And the examples for these systems are of this form. So because we have a binary task here with valid and invalid Sudoku grids, we're representing this valid example as a positive example for FASLAS. And then we are transforming, perform a small transformation on this weight penalty. So you see it's 78 here, instead of 0.77. And this is just because the ILASP systems and FASLAS systems require the weights to be greater than 0. And we have our contextual facts, which are based on the symbolic neural network predictions and metadata. So the penalty, just to sort of give you a little bit more intuition on that, this is really important because it, in the ILASP and FASLAS systems, it is paid for learning a hypothesis that does not cover a particular example. So the aim here is that we want to have contextual facts that are correct with high weight penalties. So the symbolic learners are encouraged to cover that example with the learned hypothesis. Okay, so in terms of evaluation, the real sort of interesting piece here is trying to test out this interface when we might have incorrect predictions with high confidence. So we have two neural networks. We have a standard CNN with a softmax layer, and we also have an uncertainty-aware neural network called EDL-Gen that is able to better sort of express its uncertainty in the presence of distributional shift. So we compare to neural and tree-based models for rule learning. So that's where we're swapping out our symbolic learner, but using the same softmax CNN to process the images. And we pre-train our neural networks on standard images. And for rule learning time, we then apply distributional shift to a percentage of training data points. So you can think of this as like a sort of evaluation of trying to run ILP from unstructured data in the wild in the current form, where you would have to take pre-trained neural networks off the shelf for your images that you have. So the first task is the Sudoku task, where we have our input here, and the goal is to learn the constraints of the Sudoku grid. So that's the same digit can't appear in the same row, column, or block. And the distributional shift is applied by rotating the MNIST images 90 degrees clockwise. So the figure here then shows the accuracy of the learned hypothesis. The black, blue, and purple lines are our approaches. The black line is with the EDL-Gen, the uncertainty-aware network. The blue line is with the softmax. The purple line is when we actually reduce the amount of background knowledge that we're giving to our approach. And in that case, it was removing the knowledge of all the cells in the grid being assigned to a particular row, column, or block. And we replace that with a sort of division predicate. So FASLAS had to work that out itself. And you can see we learn the correct hypothesis right up until about 90% of when 90% of the examples are subject to distributional shift. The baselines, on the other hand, so you can see the random forest as the rule learner is the red and the yellow orange lines. These two lines here are when the baselines were trained with 100 times the number of data that we were trained with. So on the same data sets, the baselines completely failed to solve this task and actually required a lot more data to get close to the level of accuracy that we can achieve in a sort of our neural-symbolic integration. And you see the baselines actually deteriorate as you go through, whereas we maintain this level of accuracy until a point in which we can't learn anything useful anymore. Okay, second task is follow suit winner. So 4 playing cards, 1 for each player, and the label is the winning player of the game. In this case, and the symbolic part is to try and learn the rules of the game, and that is the winner is the player that plays the highest ranked card with the same suit as player 1. So in this case, player 4 is the winner, we're assuming ace is high. So we've then, for distributional shifts, we pre-trained the neural network on standard playing card images, which is the sort of top left cards you can see, and then replaced these images at rule learning time with images from alternative decks. So we have a Batman Joker deck, a Captain America deck, and some adversarial decks where you can't quite see that on the slides, but the background contains the images from the standard playing card set, so from within the distribution of the neural network. So we're deliberately trying to fool the neural network into predicting incorrectly. Notice, by the way, as humans, we can completely deal with such perturbation like this. Now, there's too many of these to analyze, so I've picked 2, a minor shift and the major shift with the adversarial deck. And you can see the major shift is more challenging because the accuracy of all of the approaches actually decreases compared to the Batman Joker deck. But again, we're learning the correct knowledge up until high percentages of these examples are subject to distributional shift. I'll move quickly because I'm running out of time. So this is just looking at the difference between the EDL-Gen and softmax with higher shifts. It does actually provide a small advantage. We've evaluated this with real world data sets as well, and we get similar results. So just to wrap up then, we're able to learn accurate knowledge in distributional shifts, even when softmax inflates the confidence estimates. And we also outperform the baselines with significantly less data. Now, just before I open up for questions, we are working on a sort of end-to-end approach to lift the naughty assumption that Richard identified on pre-training. So watch this space for news on that front. So thanks for listening.